everyone! Today's video shows you how to use the ESP32 development board with a 7-inch screen to display the data of the light sensor. This small board is a light sensor. You can see the circular part with some Z-shaped traces above. This is the light sensing part of the sensor. Then this small board is some supporting circuits. You can see that there is an adjustable device. The dynamic range of the output of this sensor can be adjusted. This sensor contains 4 pins. These 4 pins include power, ground, then DO and AO. DO is its digital output part. AO is its analog output part. We connect this sensor to the ESP32 development board through DuPont wires and breadboards. We are using a relatively large ESP32 development board. The screen of this development board is a 7-inch screen. The diagonal length is 7 inches. Then it is a high resolution of 800*480. The MCU of this development board is an ESP32 module, which has Wi-Fi and Bluetooth functions. The flash of this module is 16M, and the PS RAM is 8M. As you can see, we run an LVGL interface. The entire interface runs very smoothly. The data shows that it is very smooth. The following is a brief introduction to how our entire experiment was implemented. First, we use this light sensor to collect data. We connect the light sensor to the development board. You can see that the 4 pins of the light sensor are connected via DuPont wires. Our development board is relatively large and is connected through pins. Connect this development board to the breadboard. Everyone, take a closer look. You can see that this is a row of pins. This development board has already led the GPIO pins, power supply and grounding pins to both sides of the development board. We use some of the pins on this side. The following 2 pins correspond to power and ground respectively. Above are the 2 GPIO pins. We connected one to digital output and one to analog output. If we cover the sensors, you can see that one of its indicator lights is off. After turning on, the indicator light is on. So it has 2 LED indicators. One is the power indicator, and the other is the switch indicator. Close it completely, and its indicator light will turn off. Of course, the screen color will change on my ESP32 development board. You can see that its data also changes accordingly. Let's take a look at our development environment. We use Arduino for development. Open up Arduino. We used Arduino to develop the entire program. We now also use Arduino to output its analog values. You can see that this waveform is displayed here. Let's enlarge the code. We designed a chart in LVGL, namely charts. A small chart control to display our data. This chart screen is smaller. The length and width are both 100 smaller, because if it is the same size as the screen, its coordinate scale cannot be displayed. The following code is the middle alignment. We place the chart in the center of the screen. Then there are the ticks for the x-axis and y-axis. That is, some tick values corresponding to the coordinates. We set a range for its y-axis. It is 800 to 480. Something needs to be explained here. The dynamic range of different sensors may vary greatly and is uncertain. We can generally change the dynamic range of its y-axis through some settings of LVGL, including a change in the x-axis. Here we can observe through the data collection function of Arduino. We dimmed the light sensor. If you cover it with your hands, its value will become larger. Release it and the value will decrease. Then through this function on Arduino, we can roughly determine the dynamic range of the sensor. Then write a dynamic range in the code. That is the approximate range of its y-axis coordinates. Of course, you can modify this dynamic range according to some beautification requirements. Because the dynamic range of different sensors may vary greatly, including our sensors, it is a linear change. It may also be a nonlinear change. If it is another nonlinear change, then the log value may be used instead. When we initialized the sensor, we wrote some dummy values to output to this chart. That is to say, when there is no sensor value input. This chart will also show a curve. Let's look at the main loop. In the main loop, we use analog read to read the analog values. You can see that we are the analog value of GPIO 1 pin. If you need, you can also directly convert this analog value into the corresponding voltage value. Because analog read reads the value of ADC. The ADC of the ESP3 to S3 here is a 10-bit ADC, so this value is 1024 to 1, which is 1023. Of course, different sensors may have relatively large changes in this value, including sensor drift, other problems affecting. You may need a complex tuning and calibration process to determine the actual dynamic range of the sensor, that is, the corresponding voltage value. Include this data in a calibration curve that your sensor manufacturer may provide. In addition, you may also need to use some instruments to calibrate your own sensors. Of course, for simpler sensors, or your application does not have to hide data requirements. You can directly use this data to do some simple control. Here we directly use the ADC value. You can take a look at the range of our ADC values. Under natural light, that is, the state in which we recorded the whole, we turned on a lamp. The current state is about a dynamic range of about 1,200, and the maximum may be 1,600. Anyway, my hand here has some influence on it. You can see that it gets smaller when I move my hand away. Then put your hand within this range, and it will gradually get bigger. Then I completely took the sensor and covered it. After covering it, the value will become much larger. Such a sensor is completely affected by light. Depending on the light, it will have a value change. You can see that the weaker the light, the higher the value. Of course, this value can be fine-tuned by the sensor itself. If you need to adjust it, you can adjust it. In addition, this sensor itself can also be used as a digital switch. It has a digital input, because the digital input has only a range of 0 to 1. The control may not be as flexible as analog. For example, the digital quantity may be wrong. because it also uses a value to determine whether it is on or off. Then the analog quantity is a continuously changing quantity. We can control more accurately through analog quantities. Such a light sensor can control the light switch, for example. We can use this analog value to adjust the brightness of the light. We can apply this kind of light to the most common smart agriculture. It can also be used in smart homes to control the opening and closing of curtains. For example, if the light is strong now, let the electric curtains block the sunlight on the window to make the light in the room softer. When the light is weak, we can open the curtains completely. Let more natural light into the entire space. Through such an experiment, we can see. We use the sensor to make an input. Then I use the ESP32 to S3 development board to make a processing platform. Including data reading and display are all done on this development board. We can also make further expansion. For example, we can adjust the Y-axis range and X-axis range of the LVGL interface. You can make some small controls to adjust. It can also be based on some of your needs. For example, you can collect this lighting data and store it in an SD card. This development board has an SD card slot. We can insert the SD card into the SD card slot. Then store some of the data we need. Overall, this is a simple process of collecting instruments. A simple instrument that integrates data collection, storage, and display. Okay, that's all for today's video. Thank you for watching.